restoring force method. Okay. So it is not a new method basically. So just I'll take the example that we have taken already. Suppose if I have a spring block system in vertical plane, then what we did was at equilibrium, the spring will be having some extension, suppose x naught, that will be equal, kx naught will be equal to mg. And then if I'm going to provide an additional displacement x from the mean position, then what all forces that will be acting on our particle will be kx plus x naught and mg, no? So maybe I'll write it down as forces that are acting on this block are kx and kx naught, upward and mg, no? And kx naught job is to cancel mg, no? Right, so if I'll ask you write down the net force in the down direction, that will be mg minus kx naught cancelled by mg. So the net force is only going to be minus kx. So whatever the net force is only due to the additional displacement, not displacement, additional extension and oh. Goodness. So net force is only due to the additional extension of the spring from the mean position or not. So what really the net force is going to be, that net force will be the force only due to the displacement from the mean position. So what you do, you don't care about, if I'll ask you which force in this case is responsible for this block to undergo SHM, it is the spring force. Then you just consider the spring force that is going to come into picture just due to the displacement given to the block from the mean position, that will be coming out to be kx. That will be the force which is going to be our restoring force, no? So the restoring force is force only due to the displacement from the position of equilibrium or mean position. And whatever this force will come, it will be acting opposite to the displacement, no? And it will act. So from now on, you don't have to write the force equation at the mean position. Just you consider writing the force that is going to be only due to the only due to the extra displacement that we have given from the mean position. Maybe I'll take one more example. Suppose if the question that we did in the last class, we had a block hanging with the help of a spring. And what you do, just you consider which force will make this block to undergo SHM, spring force. So what will be the spring force due to the displacement x given? That will be kx upward. And down I have taken as positive, so the net force will be equal to minus of kx. And restoring force I will write down as, it will be kx. The one that will be the force that is going to come into picture due to the displacement given from the mean position. So I hope you got the idea what really I'm trying to convey here. Okay, please copy this thing. So maybe if I'll solve this question, the one that we were having, this block oscillating, no? which is, so we can solve it by restoring force method also. So restoring force will be the force that is going to come due to the displacement I am going to give from the mean position. Suppose if I displace this block further by x, so tell me which force causes SHM. So in this case, force responsible for SHM is the buoyant force. So buoyant force only due to the displacement x given to the block from mean position will be how much? So this is a block whose area of cross section is A. And if I depress this block into water by suppose length x, so the volume of the water displaced due to this x displacement of the block will be area of the cross section into x, no? So volume of water displaced due to the displacement x will be how much? A into x. So the buoyant force due to the displacement x will be how much? It is the weight of the water displaced. It will be rho ax into g. So the restoring force is going to be here rho ax into g. And which way that restoring force will act upward? So, but which way I have given the displacement down? So down, taking it as positive, if I write the force equation, it will come minus of rho ax into g. F I can write down as ma, which will be minus of rho ag into x. So a will be equal to minus of rho ag by m into x. So still we are going to get same answer, no? I hope all of you understood, no? Maybe I'll go back to the previous page if you have not copied. Copy this thing. So if you want, I can repeat those who have joined after some time. So this is the example that we have taken already. We have got a block hanging in the vertical plane with the help of a spring, as you see in the figure. So as you can suppose, if I consider the extension the spring is going to have at the mean position is x naught. So kx naught must be the one which is balancing gravity. So kx naught equals mg. Then I provide a displacement x to the block in down direction. The new extension the spring will have will be x plus x naught. So spring force that will act will be kx plus x naught. mg acting down. And in finding the net force in the direction of the displacement, which is down direction, it will be mg minus kx naught. So kx naught will be cancelling mg. So net force you see is only due to the displacement x given to this block, no? So restoring force will be the force only due to the displacement given to the block from the mean position, and force, and which force I'm talking about? The force which is causing this block to undergo SHM. So this spring block system kept on an inclined plane. If I further pull the block down the incline by x, what is the force only due to this displacement x will be kx upward. So net force will be minus kx. So after that everything same as is 1. So here from the mean position I am going to further push this block into the water by x. So due to that displacement x given, for whatever buoyant force that will come into picture, that will be the restoring force, which will be acting opposite to the displacement given. So the volume of the water displaced due to the displacement x is A into x. So the buoyant force due to the displacement will be the weight of the water displaced, which will be rho ax into g. So restoring force will be rho ax into g, which will be acting upward, opposite to the downward displacement given. So with sign convention, taking down as positive, force will be this much. ma equals minus of rho ag into x. A will be minus of rho ag by m into x. So whatever is the coefficient of minus x, that is our omega square, which will be rho ag by m, no? So I hope all of you got this restoring force method. Okay. So I'm going in a little bit different order, not the way the order is in our beginner boxes. So till now, whatever examples we have taken, everywhere the particle was undergoing pure translational motion. No? So that's why we call it as also as linear SHM. Means the kind of motion the particle is having is translational motion, so we call it as linear SHM. Next thing we'll see angular SHM, like in the case of pendulum. So there the object or the rigid body will be undergoing pure rotational motion. So we'll do some questions before we go for some polls. So we have got a setup of ideal pulley. Ideal string means the string will be slipping around the pulley, not causing the pulley to rotate. And if I pull that block by some amount and then I release it from there, it will be undergoing SHM. And we need to find what will be the time period of the SHM at the and I'll wait from it. So first method will be the original one where we write down things at the mean position. No? So at mean position, first of all, you tell me which force is going to be the immediate region for this block to undergo SHM. On pulling this block down by some amount, the spring force will change. And due to that, the tension in the string will change. So tension in the string is the immediate region for this block to undergo SHM. Correct, no? So at mean position, suppose the tension was T0 and the spring extension was X0. Suppose at mean position, the spring extension is X0. So the tension in the spring will be same as the tension in the string, which will be Kx0. And if I draw the free body diagram of the block, tension on the block acting upward, mg acting down. So T0, which is Kx0, must be equal to mg0. That is step 1 basically. Next, what we do, we displace the block through some amount. Suppose if I displace the block in down direction from the mean position, suppose. If I displace the block down by x, tell me by how much amount the spring will get extended. Same amount? Same amount. Now the tension the spring will be having now will not be x0, it will become x0 plus x, correct? So the tension in the spring, which will be same as the tension in the string, which will become kx plus x0. Now again I will draw the free body diagram, which way the tension will act now upward and other force mg remaining same only, and which way I have given the displacement down. So I'll consider down as positive as sign convention to write down the net force. So net force acting on our block will be mg minus t, which is kx plus x0. So what we get is F will be equal to mg minus kx minus of kx0 from equation number 1, that is kx0 equals mg. I can cancel mg with kx0. What we get, net force ma to be equal to minus of kx, a will be equal to minus of k by m into x, omega square coming same as we have seen some examples before it. So this is one method. What will be done if I use restoring force method? By restoring force method, if I solve, So the force responsible for SHM here is which force elbow? Tension. So the tension due to the displacement will be equal to the tension in the spring due to the displacement x. No? So what will be the spring tension due to displacement will be kx. So restoring force will be kx, and restoring force, we know it acts opposite to the displacement x given. No? So what will be the net force? Minus of kx. No? It's simple like that. So after that everything will be same only. I hope you understood the restoring force method. So here mg remaining constant, not going to be the one which is responsible for and making this block to undergo SHM. So the force which varies is the tension force. So tension force is the one which is making this block to undergo SHM. Just we'll find what will be the tension in the string due to the displacement x given. So the tension in the string due to the displacement x given will be same as the tension in the spring due to the displacement x given, which will be kx. So the tension in the string will be kx, which will be upward, and that will be the restoring force. Correct? No? I hope you understand this way. Because we are avoiding that cancellation in mg because we know it will get cancelled. So why to write it in the first place? So it's not a new method, no, just we are avoiding some calculation. Next question, to be able to solve that, you must remember that moving pulley method. Okay, those who are online, I can take a new page. Maybe if you have copied, if you have not, you tell me, I'll return back. So what was that moving pulley method? Suppose if I have the pulley and if I take a case, suppose if pulley is having a displacement xt upward and maybe the velocity the pulley is having vp upward and the acceleration the pulley is having is ap upward, and any point on the left side of the string is suppose having a displacement x1 upward, and let's suppose velocity at any moment it is having v1 upward and acceleration a1 upward, and any point on the right string is suppose having displacement x2 down, velocity v2 down and acceleration a2 down. So what was the relation in general was xp will be equal to plus minus x1 plus minus x2 by 2, no? Vp was equal to plus minus v1 plus minus v2 by 2, and ap was equal to plus minus a1 plus minus a2 by 2. If I give you the case, which is this one, what we have is, you see, xp and x1 are in the same direction, and xp and x2 are in opposite direction. So whichever are in opposite direction, so here x2 is in opposite direction to xp, so in front of x2 we will be having minus. Here x1 is in same direction as xp, so in front of x1 we will be having plus. So in this case, for this particular case, if I'll write down xp will be equal to x1 minus x2 by 2. Same thing goes for vp, which will be equal to v1 minus v2 by 2. AP will be equal to A1 minus A2 by 2. We'll take one more example.
And that.
For the pulley is having XP displacement upward, this point has got X2 displacement down in same time, and any point in the right side of the string has got X2 displacement upward. So here relation will be xp equals minus x1 plus x2 by 2 or x2 minus x1 by 2.
Again.
That moving pulley maybe was of not much use in laws of motion, because always we had some another method also to get the constraint apart from this moving pulley method. But in here it is going to be of use. So in this case, again it is given we have got an ideal pulley. And we need to determine what will be the time period of the SHM this block will perform. If we pull the block by some amount, then we release it from rest. So maybe I'll try doing by restoring force method first. So the restoring force will be the tension in the string only due to the displacement x of the block from mean position. So suppose if I displace this block down by x from mean position, whatever the tension in the spring that is going to be, that we can figure out only when I know what will be the extension of the spring. No? So what we have is whatever amount by which the pulley will move down, by same amount our spring will move down. And if this block is going to move down by x, then any point in the right string will be going down by x. No? And if I take any point in the left part of the string, it is something which is fixed to one end. So what really the displacement any point in the other part will have? 0. 0, no? You take any point in the left string, how much displacement it will undergo? 0. Why? Because it is fixed to the other end, no? Because if I'll ask you what really this length, blue length is it going to change? No. So what will be the displacement of that point? Will be 0. Now what I have is, suppose if I assume that pulley came down by xp, this point coming down by 0, this point going down by x. So what was that pulley constraint? xp will be equal to 0 plus x by 2. So what we have got is xp will be equal to x by 2. So this is the extension of this spring only due to the displacement x. No? So what really will be the spring force due to this extension of the spring will be kx by 2 or not? So extension of the spring is x by 2. So what will be the spring force? Kx by 2. And tension in the string on the other side will be same because it is an ideal pulley. And ideal means massless. Massless means net force 0. So if I have net force 0, then 2t must be equal to kx by 2. So what t will be equal to? Kx by 4. And this will be our restoring force or not?
Yeah.
Because this is the tension that is going to act due to the displacement x given. No? If this is the restoring force, then we know that restoring force is the force which will be acting opposite to the displacement. So net force is always minus of that. It will be minus of kx by 4. Mass of the block m, so ma equals minus of kx by 4. So what really A will be? Minus of k by 4m into x. So what really is our omega square? K by 4m. So omega will be root over k by 4m. So t will be equal to 2 pi root over 4m by k, no? Or maybe I could write it down as 2 pi root over m by k by 4, no? Correct. So now So maybe we can do something about that. So this spring block and pulley setup, whatever time period it is going to give us, same time period is going to come. If I use only one spring, just I keep the spring constant to be k by 4. No? So I can say this is kind of an equivalent system for the given system or not. Suppose I want to get same time period but using a spring block in the vertical plane. So what should be the spring constant I must utilize or I must use for the k by 4? Understand this thing? So in this case, the object will be undergoing pure rotational motion. So when we say in case of linear SHM, the particle will undergo SHM when the force was going to come proportional to minus x. So here we'll say the torque must come proportional to minus of theta, or the angular acceleration should come proportional to, and we'll write down alpha looks like the angular acceleration must come proportional to minus of theta. Theta is the displacement from mean position. And minus sign indicating that angular acceleration acts opposite to the angular displacement. No? And same way, whatever was the coefficient of minus x here, coefficient of minus theta in the expression of angular acceleration will be our omega square. So I'll take the case of simple pendulum, suppose. Steps will be same only. First we will decide the mean position and we'll write down force equations and torque equations if necessary at the mean position. Suppose if I have a point object or the pendulum bob, so what really will be the mean position when the string will be vertical? Because in this case at mean position, particle undergoing pure rotational motion, what must be 0? Net torque must be 0. So net torque will be 0 when only when the string is vertical. Suppose if I displace it by some small amount from the mean position, so whichever way we are going to provide the displacement, that will be taken as positive for the sign convention. So see, I am going to give a displacement from the mean position by an angle theta, and what really is the sense of that angle theta is anti-clockwise. So anti-clockwise will be taken as positive for the sign convention. Then we draw the forces acting on our block particle, tension force acting like that, mg acting down. And about which point it is undergoing pure rotational motion, about O. So about O, if I ask you to calculate torque due to the tension force will be 0, because you see the line of action of the tension force, it is intersecting it is crossing the point of suspension. So torque due to T0, only torque we are going to have is due to mg. So to find torque due to a force, I can find the component of the force that will be perpendicular to the radius vector. So radius vector will be of length same as the length of the string, suppose it is L. So what will be this angle? Can you tell me? This angle theta, this will be 90 minus theta. So this will be 90 minus theta only. Can check that. So component of the mg perpendicular to the string length is mg sin theta. And the torque due to mg, you tell me in which sense it is going to act. Clockwise sense. So that will be our negative sense for us. So torque due to mg will be minus of F perpendicular into mg. F perpendicular is mg sine theta into L. So you see, torque is not proportional to minus of the angle theta, no? So it's not going to be undergoing SHM. So it's only going to undergo SHM when torque must come proportional to minus theta. And that can be possible only when sine theta can be written as theta. And that can be only possible when theta is very small, no? So it's going to undergo SHM for very small angle. The motion is SHM, no? Correct? For finite angle or for finite angular displacement theta, it will be an oscillation but not SHM, no? It will be oscillating, that is correct, but it is not SHM, correct? So what is the torque? I can write down as moment of inertia into angular acceleration, I alpha. And theta very small, so mg sine theta will be same as, or sine theta will be same as theta, so it will become mgl into theta. So what really alpha will come? Minus of mgl by I into theta. And so what really will be the omega square? That will be mgl by I. And what is the moment of inertia of a point mass, which is connected using a string of length L about O, will be ml square.
Mars.
mr square, R is in ml square. So mgl by ml square. So 1 L gone, m gone. So it's going to become g by n. So omega is going to come root over g by n. So time period will come 2 pi root over L by g, that you're supposed to remember even as a result, and that you can't forget. No, man. Time period will have 2 pi and will have root over something, either g by L or L by g. If I use L by g, then only the unit of time period will come second. So it must be root over L by g. No?
Yeah.
Now, something called physical pendulum. Suppose if I take a laminar object, be something like calendar, and then I hang it, or then I pivot it in vertical plane about some point O. There is a point about which it is free to rotate in the vertical plane. Then at the position of the equilibrium, what you will find, the center of the mass or the center of the gravity is going to lie on the vertical line which is passing through the point of suspension. Folklore. At the position of equilibrium, the vertical line passing through the suspension point must pass through center of the mass or center of gravity, because then only I can have net torque 0, no? Suppose if I'll ask you what all forces that will be acting on this particle will be a hinge reaction that will act upward at the point of suspension O. And there will be another force which will be gravity acting down. And since it is under force equilibrium, since it's not going anywhere as a whole, so that H hinge reaction must be equal to mg. So what I have is two forces which are equal and opposite, and their line of action is not same. Okay. And that point of application is not same. Only when I can have torque due to them in total to be 0, when their line of action must be same. Suppose if I take a rod and then I suspend it about some point which is one of the end. Then at the position of the equilibrium, mg, is it not the center of the mass, is it not lying on that vertical line tracking at the point of suspension? Because if not, it will result into a net torque. Suppose if I displace this object, maybe I'll take a rod only. And in the position of equilibrium, the vertical line passing through O must be passing through the center of the mass also. So if I displace this rod to a new position, now it will make, if I'll ask you determine the torque due to, or whatever net torque we are going to have about the point O. If I displace it through some angle theta, you see we are going to have a torque acting on this rod about point O, which will be due to mg only. Torque due to whatever hinge reaction, if there's any, will be 0. So it can stay under equilibrium only when net torque will be 0. That is only possible if mg line of action is same as the line of action of the hinge reaction. So I can take a new person, move it. It's similar to earlier thing only, nothing different.
You have the measuring effort.
Maybe I'll continue and say, having a new question. So this is my random shaped object which is hinged at about point O, and at the position of equilibrium, center of the mass will be lying on the same vertical line. Now if I displace this object to a new position, same arbitrary shaped object it is, just I'm shifting it by rotating it through some angle theta. Now center of the mass will be at some new position here, suppose. But mg will be still acting down. And suppose the distance of the center of the mass or the perpendicular separation between the center of the mass axis and the axis passing through the point of suspension O is suppose x. And if I have given displacement theta, so what is the component of the force perpendicular to the x is mg sine theta only, no, same like earlier. So the displacement, angular displacement given, it is in anti-clockwise sense. Torque is going to act in clockwise sense. Torque due to mg will be minus of mg sine theta into x. Torque about point O I have to consider here, which will be I alpha. That will be equal to minus of mg. If theta is small, then it will become mg x into theta, no? So alpha will be equal to, this is not that x, no, we have to it is theta, which is the thing we are supposed to consider here, no? It's not that x, no? So mgx by I, so what really will be our omega square? That will be mgx by I, no? And what really I is, I can write down as ICUM plus mx square, no? Where x is the perpendicular separation between suspension point and center of the mass, no? And suppose if I write down moment of inertia in terms of radius of the gyration, which will be mk square plus mx square. So omega square is going to be equal to mgx by mk square plus x square. See getting cancelled again here. Where k is the radius of gyration, about center of the mass axis. This way also you can get the result. But suppose I want to keep in that format only. Omega will be equal to root over mgx by I. So time period will be 2 pi I by mgx. No? In case of simple pendulum, I was equal to ml square, x was equal to L only. No? We had a point mass only attached at the end of a massless string of length. So what is the distance of the center of the mass of that point object from the suspension point is length of the string only. So for simple pendulum, I was ml square and x was L only. So we got L by G. And for simple pendulum, same like physical pendulum, nothing much different, no? Easy only. So for just a simple example, if I give you a uniform rod suspended about one of the end, uniform rod means center of the mass will be lying at the geometric center of this rod. So what really the x is going to be here? X will be L by 2, no? So here x will be L by 2, moment of inertia about the point of suspension, we know it is ml square by 3. So time period will be 2 pi ml square by 3 by mg L by 2, which will give us 2 pi root over 2L by Gg, no? And if it is easy only simple pendulum, nothing much in there.
Oh. And then pounds. Football.
Okay, you can take a new place.
And then you were not on the and then power. Yeah, she's they didn't so I keep up.
Big step before I start HSM in combined motion, few small things I'll tell you. Suppose displacement, I'm writing it down using x, which is a sine omega t plus phi. Then the velocity will be a omega cos omega t plus phi. So from this thing I can say maximum speed is going to be equal to a omega, no? So what we have is, suppose if I write down x is going to be equal to a sine omega t, and I want to figure out cos omega t. So cos omega t plus phi is going to be root over 1 minus sine square omega t plus phi, no? And sine is omega t plus phi is nothing but our x by a. So it's going to become x square by a square root over, correct? On the, what really is our v by a, it is the one which is v by e omega, no? V by a omega is our cos omega t plus phi. Well, square of both the sides, so we get v square by a square omega square will be equal to 1 minus x square by a square. So what we get is x square by a square plus v square by a square omega square is going to be equal to 1. So what really the curve I will have if I plot x versus v, it will be an ellipse or not? Yes. Fine. There is what we can call it as a relation between
Deep center from the
correct.
B square, the space square, then B.
Sure not?
Then we is colored. Like the diesel feature. Second dynamic ground. Second use the
Plus 2 ways only.
OV.
So up to beginner box. 3 you can solve all the questions. Beginner box 4.
The school and I'm not like it to liquid thing is. The most initial stuff. And my mouth was in the other way. And the other hand. I use another nerve.
Okay, continue please.
Sir, what topic would we be?
Prince,
Well, what is?
it's not over, man. Not over. Suppose if I have two body system, we did something like two body system in center of the mass chapter, no?
So,
That is.
Suppose if I take a case of two block which is connected by an ideal spring, placed on a smooth horizontal surface till the spring is compressed and suppose if I compress the spring by some amount and the blocks are released from rest. So tell me, what will be the velocity of the center of the mass after releasing the blocks will be? Suppose if I compress the spring by pressing the blocks M1 and M2 from both the sides. Right now, suppose if I press M1 and M2 from either side, so as to compress the spring by some amount, and if I release it at some compression but from rest. So what will be the velocity of the center of the mass afterwards? Will be zero only or not? Because the moment I am going to release it, at that moment, what is the speed of every block is having? Zero. So if I consider M1, M2 and the spring, which is massless thing only, as our system, what is the net external force acting on the system I have got along horizontal? Zero. And what is the initial velocity of the center of the mass will be just after releasing it? Zero. Correct now? So what will be the velocity of the center of the mass? Will remain zero only. Means M1 and M2 will move, but center of the mass will not be moving at all. Somehow M1 and M2 will move in a manner so as to keep the center of the mass stationary. So in this case, what happens? Both the blocks will undergo SSM about the center of the mass, and the time period of SSM I will tell you, then we will derive it again. No?
Both are compressed like.
So I compress the spring, no, not both are compressed, it's not making sense. I compress the spring, maybe I press the blocks from either side with equal force. Then suddenly I release it from rest. Suddenly after releasing it from rest, what is the speed M1 and M2 or velocity M1 and M2 will be having just after releasing it? Zero. So initial velocity of everything in the system zero. So what will be the initial velocity of the center of the mass? Then zero. And after I am not applying any, the moment I release it, I am not applying any force on it along horizontal. And the spring force internal only, we don't need to worry about that. Net external force zero. So what will be the acceleration of the center of the mass? Zero. So what will be the velocity of the center of the mass? Will not change. So it means M1 and M2 will move, but it will move in a manner such that center of the mass remains stationary. So, and they will be oscillating even, but they will be oscillating about the center of the mass, and with some time period that we'll figure out. So the blocks who will undergo, I'm writing the result that will prove it also, will undergo SHM, and the time period of the system will be, suppose if I had one block and one spring system, what was the time period? 2 pi m by k. So now time period will be 2 pi mu by k, where mu we call it as reduced mass. and that will be equal to m1 m2 by m1 plus m2.
Alcohol. Is or because
So this is our center of the mass. At any point of time, suppose m2 is at x2 and m1 is at x1, or m1 is displaced by x2 and m1 is displaced by x1. So at this moment, if I'll ask you, what really will be the change in the length of the spring will be? x2, suppose x2 is 2, x1 is 3. So it will be 2 plus 3. But x1 in vector form, if I am going to write down, considering one side as positive, suppose this side is positive, what I must write down? x2 minus of x1. m1 m2 by m1 plus m2. m1 m2, forward m1 m2 by m1 plus m2. Plus. Plus only. Minus means equal mass infinity. Minus was not there. So the extension of the spring, suppose at any point of time, the displacement of m2 is x2, displacement of m1 is x1. So extension of the spring with sign convention will be x2 minus x1. No? It is vectors only, just it is 1D, so we use plus and minus. That does not mean they are not vectors. So maybe you write down like vectors only. x2 minus x1. So what is the force that will be acting on m2? That is only the spring force. Suppose if I consider m2. And which way the spring force will act? Suppose the spring is elongated in total by x. So the spring force will be kx, and that kx is going to act this way on m1. The same kx will act this way on m2, and this is how it will be acting on the other side of the spring. So what is the force that is acting on our m2 is F this way. And which way it has got displacement from the center of the mass, which is a stationary point. Stationary point means it is a point in ground frame only. So how much displacement m2 has got? x2. So what is the force it is having now? It is, this I am calling it as x, suppose. It is minus of kx if I consider the direction of the displacement x2 given to m2 as positive.
Plus.
And force I can write down as the time on m2a2, no? m2a2 will be equal to minus of kx. And if center of the mass is going to be remaining stationary, so displacement of the center of the mass will be 0. So m1 x1 vector plus m2 x2 vector by m1 plus m2 must be equal to 0. So m1 x1 must be equal to minus of m2 x2. For magnitude of m1 x1 must be equal to m2 x2. No? So the extension x, if I write down using the length x1 and x2, it will be x1 plus x2. No? Magnitude of x1 and x2, if it is x1 and x2, then what will be the extension? It will be x1 plus x2. Then what I can do, I want to get things only in terms of x2. So I will replace x1 in terms of x2. So x1 equals m2 by m1 into x2. And that x1 I can plug here. We can get m2 by m1 into x2 plus x2. What it will become? m1 plus m2 by m1 into x2. So we get m2a2 to be equal to minus of k m1 plus m2 by m1 into x2. So what acceleration a2 is, it is minus of k m1 plus m2 by m1 m2 into x2. Correct? And what really is our mu? Mu is m1 m2 by m1 plus m2. So what really it will come? K by mu into x2. So a2 is coming proportional to minus of x2. So whatever is the coefficient of minus of x2, that is our omega square, which is k by mu. So omega will come root over k by mu. So what time period will come? 2 pi root over mu by k. Same way you can consider m1. Write down the forces, time period will come same and must come same also. Because in the time in which m2 will move to the rightward extreme, m1 must move to leftward extreme. Correct? And they should complete each oscillation in same time, then only the center of the mass can remain stationary at one place. And the amount by which they must move must follow this equation. m1 x1 must be equal to m2 x2, then only center of the mass will remain at rest. In vector form I see m1 x1, is it not opposite to m2 x2? I hope you got this point. Okay, no? Yes. Or know this? Then just one example, then I'll leave you.
Right. And model.
Then get to code.
This is L-shaped block of mass m2 kept on a smooth horizontal surface. And here I have m1 connected to it via a spring. And this is a smooth surface, and the surface between them is also smooth. So what kind of system it is? Two-body system or not? If I compress this spring and then I release it from rest, or I elongate the spring by pulling m1, m2 up, and then I release it from rest, time period will come same as earlier one, only 2 pi mu by k. You should know, same thing now, and just both of them were lying on the ground. Now one of them. Okay, all of you should know.
We're on there. Straight up. We saw what I'm doing. Then we're gonna move around.
Okay, we'll end the class. Okay, then bye everyone. See you in the next class. So tomorrow, whether we have this extra class or not, I will tell you before 2 p.m. tomorrow. Okay, so check your WhatsApp group tomorrow. Okay, now.
Yes, that's all.
Okay, bye.
You bring the one here, coming right here. Put in the word of the dirty. I saw them.
Today is 31st.